This is 2D from your activity packet. So we're supposed to sketch what the NMR spectrum of this compound might look like. So what we have here, we have these methyl groups all bonded to the same carbon, and this single bond is able to twist. So really all these CH3s are equivalent. There's nothing making one CH3 group distinct from any other. So all three of these hydrogens, all three of these H3s are equivalent, and they're going to be responsible for one signal. And that's probably going to be around 1, maybe just a little bit downfield of it, because these methyls are somewhat in the vicinity of this functional group here, the carbonyl group. So that'll pull it just a slight bit to the left of 1 maybe. So the question is, before we can finish drawing the signal, what is the splitting? Well, the question is how many hydrogens are within 3 bonds of any one of these H's up here. So the answer to that is 0, because there's no hydrogens bonded to this carbon. So this carbon serves as a buffer, and it keeps the methyl hydrogens from getting split at all. So this is just one gigantic singlet with a huge integration line to indicate there are 9 hydrogens that are causing that signal. The other 3 hydrogens in here are over here on this CH3, and the carbon that the hydrogens are attached to is bonded to an oxygen, so that the oxygens are electronegative, and that's going to pull the signal significantly far downfield. When this oxygen is part of an ester functional group, as it is here, you might get even sometimes a little bit more than 4. So let's start to make a signal here, but what's the splitting going to be? Again, these hydrogens are buffered from any other hydrogens, so they're nowhere near being within 3 bonds of other hydrogens. So again, not split. We get a singlet, 1 peak, and the integration line would be smaller, but enough to indicate there are 3 hydrogens. And here's our other molecule. Let's look for equivalence here. Here we have these 2 methyl groups which are equivalent, so let's call these are our A hydrogens. Then we have these 2 methyl groups that are equivalent. Let's call them our B hydrogens. The A hydrogens are buffered from any other hydrogens within 3 bonds, so there's going to be no splitting. They're also kind of buffered from the oxygen, although they are in the general proximity to that electronegative oxygen, so I think that might pull us up to about 1.5-ish, because there are 2 oxygens in the general vicinity. So let's put a big singlet caused by 6 hydrogens right about 1.5. And then what about these B hydrogens? They are very proximate to the oxygen, so that's going to pull them up to about 4. And they are also buffered from being within 3 bonds of other hydrogens, so they are not going to get split either, so another singlet. And again, there's a total of 3 plus 3, 6 hydrogens in there. Alright, well, we're all here. Let's just hammer out 54B. So, first things first, look at the formula of the compound. You can almost make that out on your sheet. C6H12O. Degrees of unsaturation, 2 times N plus 2 minus the number of hydrogens you actually have divided by 2. So this is 14 minus 12 over 2, 1 degree of unsaturation. A non-mathy way to think about it is that we would need 2n plus 2, or 14 hydrogens to be totally saturated, but we're short 2, and we know that every 2 hydrogens we're short is 1 degree of unsaturation. So there's one double bond or ring. And when we look at the IR, when we look at the IR spectrum, we very quickly figure out what that double bond is. It is the carbonyl group with a carbon double bonded to an oxygen. So there's no other double bonds or rings in this molecule. And here's our NMR spectrum. There's only 2 signals, so that means we're going to have a lot of equivalent hydrogens. And from the integration, it looks like there's going to be a total of 9 over here and 3 over here. So, because the signal on the left is at about 4 all the way downfield, I'm going to go ahead and assume that the hydrogens that are responsible for that signal are bonded to an oxygen. We know there's 2 oxygens. I had the formula wrong. 2 oxygens in this compound, and a CH3 bonded to one of them would create a signal at the right location. The signal on the right, I'm going to guess that this is due to 3 symmetrical or equivalent methyl groups. And because there's no splitting of this signal, and because it's the only thing that makes sense, I'm going to say these guys are bonded to a quaternary carbon. And if that's right, we've accounted for 5 of our 6 carbons already, and we know from the IR that we have to have a carbonyl group. So we have to put that somewhere. And from the 2 segments we know our oxygen has to be bonded to something, our quaternary carbon has to be bonded to something. It just makes total sense that that's the carbonyl carbon. So here's your answer. This molecule with these 9 equivalent hydrogens being buffered from any splitting because they're bonded to a quaternary carbon that doesn't have any hydrogens bonded to it, and they're pulled very slightly downfield from 0.9 to about 1.1 because of their proximity to the carbonyl functional group here. And then these 3 hydrogens giving a signal way up almost at 4 because of their very close proximity to an oxygen. Hey, this is exactly the same molecule as the first molecule we looked at in this video. Interesting. I wouldn't want to leave you on that kind of repeat. So here's something new. This is not an H NMR anymore, not a proton NMR. This is a carbon-13 NMR. So this is absorbing frequencies by the nucleus of a carbon-13 isotope. And a difference between the carbon-13 and the proton NMR is that in the carbon-13 there is no splitting. So all the peaks are single peaks, so you don't have to worry about splitting. But similarly, the locations of the peaks are very important. And you have this chart in your book online and on the first page of your activity handout that shows whereabouts you can expect different kinds of carbons to show signals. Okay, so let's approach this problem here. We have no degrees of unsaturation because 2 times 4 plus 2 equals 10, and we have all those 10 hydrogens. There's no double bonds or rings. First step done. What does that tell us about what functional group the oxygen can be in? Well, it can't be in a carbonyl because that would be a double bond. And this is a saturated molecule, so we can't have that. So it could either be an alcohol or an ether. Alright, now let's actually look at this spectrum. I'm seeing 3 peaks, 3 signals, and there's 4 carbons in here. So that's telling me that there are 2 equivalent carbons, because just like the proton NMR, there is overlapping signals from equivalent nuclei. And I think the only way to get symmetry in this molecule is with methyls. Just methyl is more likely to be equivalent. And we're pretty sure that these carbons are responsible for this signal because according to that chart on your activity sheet, the only kind of carbons that'll give a signal as low as 20 are going to be methyl carbons. No, there's nothing else. Judging by the formula here, there's nothing else that could be creating that signal. So what can we logically conclude about the rest of this molecule? Well, these methyls are probably bonded to a carbon. If they were bonded to the oxygen, they wouldn't be giving a signal way over here. And you may be asking, well, how do we know they're not? Maybe the methyls are bonded to the oxygen and they're creating a different signal. Well, if that was the case, the molecule would have to look like this. And that would be it, and there'd be no room for the other 2 hydrogens and the rest of the carbons, because you can't make more than 2 bonds on an oxygen unless it's going to have a formal charge, and you don't usually see molecules with charges. So not that probably. But back to our hypothesis about what these methyls are bonded to. They're probably bonded to a carbon, and we know it's bonded to some other stuff, and because we have to go on and make the rest of the molecule. So this carbon here wants 4 bonds, so it must be a CH. Before we go on, let's make one thing clear. We know that the carbon that's responsible for the signal at 70 is bonded to the oxygen, because that's how you get a signal up to 70, is by having the carbon bonded to something like the oxygen. And if you look at your little chart that shows where different kinds of carbons show up, the area for a carbon bonded to an oxygen is centered right on 70. Our chart also tells us that a CH is likely to show up from anywhere between 30 to 50. So this peak at 30 is within that acceptable range. So assuming we're right about the first part of our molecule over here, the 2 methyls and the CH, we only have 1 carbon to go, and we got to put in the oxygen. So which one goes first? Let's pretend the oxygen would go here. Then we'd have to put a CH3 over here. But that can't be true, because this would be a molecule where there's 2 carbons that are bonded to the oxygen. Then we'd see 2 peaks around 70, but we don't have that. So we're going to have to put in our CH2 here, and then the oxygen. I think it's more likely that this is an alcohol instead of an ether. And then it would make sense that there's this 1 carbon that's bonded to the oxygen, and that's causing this peak. Gosh, I hope you guys are enjoying these spectroscopy puzzles and riddles as much as I am.
Made with Doodlecast Pro.